All right, thank you all for joining us, and thank you to George, Florin, and Jacob for allowing me to speak at this. I'm going to start sharing my screen, and I'm going to start off by sharing the presentation I've got here. So I'm going to just start this from the beginning. I'm going to start this from the beginning. All right, are y'all able to see the screen? Yes, sir.
Yes, I can.
Okay. So what I can do is I can start off by talking about Simplilearn. This program that I did was through Simplilearn, and Simplilearn, it's a leading global digital skills provider, and it helps empower learners worldwide to achieve career goals. Simplilearn started in 2010, and it offers a wide variety of boot camps, online courses, and certifications, not just in machine learning and AI, but also in data science, data analytics, data engineering, DevOps, a lot of different areas. The project that I'm presenting tonight is the Capstone project for the Artificial Intelligence Machine Learning Bootcamp, which was offered in conjunction with Caltech University. I chose the healthcare option because I'm passionate about using artificial intelligence machine learning to improve healthcare. And what I'm going to mention is that I'm in no ways an expert in artificial intelligence and machine learning. I still have plenty of things to learn. This is one of the first projects that I've done using AI ML, and obviously I've still got a few things to learn here. So what I'm going to start off first of all is by talking about what is Simplilearn, which Simplilearn, as I mentioned, is an online ed tech company headquartered in San Francisco, California. It was founded in 2010, and it offers online programs for areas. And what I pursued the artificial intelligence machine learning course offered in conjunction with Caltech University in Pasadena, California. And so what I'm showing you all here, these are the courses that I took. And these are the courses that were part of the program. And what I'm showing you here, what I'm showing right now tonight is the Capstone project. So on the Capstone project, I had three options that I could choose from, which were EdTech, healthcare, and cybersecurity. And as I mentioned, I chose the healthcare option because I'm passionate about AI and how it can be used to improve healthcare throughout the world. I've been pretty interested in healthcare for a long time, learning more about it. And what I'm going to note here is that this is not real healthcare data. Otherwise, I would be in some pretty serious trouble if I used the healthcare data without being authorized to do so. I could get into some pretty major trouble for it. So that's what I'm going to mention here, because this data is fake data. And so the Capstone project was split up into 4 weeks. And so there were 4 different parts of the Capstone project. So the first part was data analysis. The second part was talking about dimensionality reduction. Third part was talking about clustering algorithms. And the fourth week was talking about machine and deep learning techniques. And I'm going to go through each of these weeks, each of those parts, one by one, and discuss them further. If there are any questions on it, we can put it in the chat, or you can ask. So I'm going to start off, first of all, by talking about the first week, which was the data analysis. And the basic gist of it is that I obtained a couple of healthcare data sets, and we cleaned the data sets to ensure they were usable for the project, merged them, and did a couple of plots and performed the null hypothesis testing. And I'm going to show some of the code as well. So I'm going to share the code now. So are you all able to see the code?
Yes.
Yep.
Okay. What I'm going to do, so obviously what I'm going to start off by doing is importing the necessary libraries I needed to use. And I'm going to go through each of these libraries that I've used and explain what I used here. So obviously I used NumPy. NumPy is fundamental for scientific computing in Python. And I used NumPy because it works very well for data manipulation statistics. Pandas is similar to like NumPy. Pandas is another powerful data manipulation library. Pandas provides data structures like data frame series, which analyze and handle the structured data. And I used Pandas as well for data cleaning and manipulation of the 2 original CSV files. And then SNS, which is Seaborn, is a statistical data visualization library based on Matplotlib. I use Seaborn to help create some of the visualizations as well, and to explore many of these relationships between the variables in these files. And then I use SciPy. It's kind of like NumPy. It's an open source library for engineering and science, but it provides additional functionality like optimization modules, integration, interpolation, etc. SciPy was used for the Shapiro test, which is in part one, as well as the one sample t test. Matplotlib, another plotting library in Python that creates visualizations, and it provides a wide variety of plot types. And it's a foundation for other visualization libraries like Seaborn. And then you've got Scikit. So we've got standard scalar, scikit-learn. So standard scalar is a pre-processing technique used for scaling features. It does this by removing the mean and scaling unit variance, which is an important step in principal component analysis. And standard scalar is useful for ensuring that features have the similar scales before applying the machine learning algorithms. And PCA was another algorithm that I used. And that is a dimensionality reduction algorithm. And it's used primarily for feature extraction visualization. And then we've got logistic regression, which is a classification algorithm used to predict classical outcomes based on the input features. And so we've also got, so these are some of the libraries that I use. And then next, what I did was I imported the data sets that we were talking about. So I have the data file and I have the labels file. So I have two files that I imported, and I got some basic information about these files. So that's what I was printing out here, with some basic information regarding the files. And obviously what I wanted to do next is print out the shape. I wanted to see if there were any null values in here. And what I wanted to do now is I wanted to describe the data. So when I describe this data, you're talking about the count, you're talking about mean, standard deviation, the minimum and maximum values, as well as the median and the first and third quartiles. And then for the labels, some unique, a basic description of the labels data set.
Explain to people what are the labels compared to the other data, so people understand what you're doing.
Explain the difference between the labels and versus the data.
Perfect. So people understand.
There are two different files that I was using.
Oh, you're doing supervised learning, correct?
Mm-hmm. Yeah.
Meaning that you know what the data is labeled as.
You know what the data is labeled as, that is correct.
Good. It's not always like this. This is why I wanted to make sure. It's
not always going to be supervised learning. In this case, yes, this is supervised learning.
And what does a gene represent?
What is what?
A gene, G-E-N-E. Gene 1, Gene 2, Gene 3, the column headers.
Well, these are just a couple different columns in here. That's just a couple different column names. And so what I was doing here was based on this criteria here. I wanted to see what kind of cancer is this, because it was classified in, you could classify it into 5 different cancers. And so that's what we have here in this labels.
All right, is there any way we could turn the background music down a little bit?
I don't hear any background music.
Oh, maybe it's coming from somewhere else. Let me check what I've got.
Yeah, I'm clear.
Can you go back to the data? You're saying that you have gene data, and which is fake. Remember, again, it's fake data, but you want to, according to the genes, you want to classify the data as a certain type of cancer, and you have 5 types of cancers, correct?
Based on what? Yep.
So the labels will have the cancer name, and the genes will be the data. Am I correct?
That's correct. You've got the data there.
Yeah,
thank you.
Probably correlates to like gene expression, how much mRNA there is of a given gene. Anyway.
Thank you.
So that's what you have here. And what I did now is I ended up merging the two data sets together using the pandas merge. And we merged on a common column here, which is the unnamed 0. And then after merging the data, took the shape, looked at the value counts as well, and then replaced, and then dropped the unnecessary column. And so now this is the merged data. So the 0, 1, 2, 3, 4 were the cancer types, and the reason why I moved those to 0, 1, 2, 3, 4 is because it would be easy. It's because on some of the algorithms, if I put in BRCA, KRC, some of the algorithms wouldn't it wouldn't run with the algorithms. So that's what I have here.
Wasn't the 1, 2, 3, 4 not really the cancer types? This is type of record because you have like 700 of those, if I see.
Well, we do have like several hundred different types of records. Yes.
Yeah, but they are all classified to 5 cancers. This is what you told us, correct?
So that's the BRCA, KRC, COAD, LUAD, and PRAD. Yep.
Okay, so you're not showing it now as like this record is classified like this record is classified like that. You're not showing it in this output 17, correct?
Let me just show you. Because we have the class column at the very end.
Now
so
you're showing it. So the class
that's
is the type of
There's 800 samples, probably 800
Mhm.
samples that are all categorized into one of 5 cancers across 20,000 different inputs.
perfect.
That's what we're doing there. And so that's what we have here. Do we have any other questions here?
Yeah, why does that last column have so many zeros in it? The gene 20530?
The gene 20530 has mostly zeros. There is one row that has the 0.586.
Oh, shit.
What does it mean to be a fractional gene? Is it just random synthetic data? So it might
This
not.
is random synthetic data.
Never mind then.
But I think in real life, it would correspond to like gene expression amounts as opposed to just like, did I find this gene or not in the sample?
Yeah.
True.
So then 0 would mean that there's none of that gene expression at all.
And so all of these were cancer. There was no non-cancer situation.
Yeah, these were. I would have to look at that. I'm pretty sure that that means all of them were at some sort of cancer.
Okay.
I would have to look at this one more time just to verify that.
For the sake of simplicity, don't get attached to the word gene. It can be biomarker. Just call it biomarker. It can be something else.
Okay, we'll just call it biomarker.
Yeah.
For the sense here.
Here it's called gene, but it's a biomarker.
Yeah, that's what we can do there. So that's what we're doing here. So this is another this is the combined data heat map. And so that is the data frame that we're pivoting here. And the class column is used as the index rows of the pivot table. And the data is aggregated based on the unique values in the class column. So that's what we have here. And so these are the different classes as mentioned. These are the different biomarkers. As Jacob mentioned, these are the different biomarkers here. And as you can see, you've got your different classes. You've got your biomarkers here.
So are they averaged or just summed?
Let me look. I'm not entirely sure if they're averaged or summed here, or if this was just the data that was found in. Like I mentioned, I would have to look at the data as well, and to give an honest answer there.
No problem.
So what I did was I then found the shape, and then I just then we have a bar plot here of all the different types and the value counts. So that's how many of each type there were. That's what you're seeing here. And this is more information here. And this is the header. This is the head, which is going to get you the first 5 rows anyway. That's what this 5 is for. That's just the first 5 rows. And then I used SNS to plot a cluster map here, which, as you can see, I tried doing it using SciPy. I got a warning here that fast cluster could be better. That's something I'd look at if I were to tweak this a little further. So this is the heat map. Is what we have
So,
here.
Can you interpret this graph a little bit? What does it mean when it's really bright for like these gene 1 and 5?
I'm gonna take this out a little bit. I'm gonna just go out a little bit here, Jacob.
Sure.
All right. I'm gonna zoom out just a little bit further. So the brighter they are, the higher this number is. And so it's based on these numbers that you're seeing here. So obviously, if we're taking gene, these are some of the genes here. And the brighter out they are, the higher these numbers are. That's what this means over here.
Yeah, but what is like a low number and a high number mean? Just like the gene expression. Oh, okay. I see that there's columns. Okay. I was missing an X. Got it.
George, think about it as biomarkers, not necessarily genes. It
Yeah,
can be
yeah,
things
yeah.
like blood
It could be
pressure, body
Dr.
temperature,
Seuss's who's its, what's
thousand
it.
things.
I was just confused without the bottom axis, but I got it now.
Okay. That answer your question, George? Or
Yeah, yeah.
okay. So that's the first part here. And so what I
Why
would
does
be
that graph gets a bit warmer towards the bottom? Like it gets cooler, and then there's another right there around like gene 18018, or does biomarkers start to increase again as you go down? Whereas it seems like everything else is sorted with the
yeah. So it just seems
biomarkers
like it's going to start off with higher values, and it's going to get lower as you're getting closer to about gene biomarker 16811.
Mm-hmm.
Once you get to around biomarker 8807, it's going to increase a little bit as well. And so that's what this is here. And so in this heat map too, I just took a random sample of 10 genes here. So I just took a random sample of a couple of these genes. We took a random sample. And as you can see, I took another cluster map of just some couple random biomarkers.
What are the tree structures that lead to the colorful heat map? I see the trees. What does the cluster map mean? Does it sort it somehow?
The trees? I would have to look into that a little bit further to see what is meant by these trees. I wouldn't want to say something and be completely wrong about it. So I would want to just look into this a little bit further.
That's good. Move on.
That's the first part of it. And then I can talk about, I did a heat map here. And so a couple of the statistical tests that I did here. And so I'm going to start first by talking about the Shapiro test. So the Shapiro function is imported from the scipy.stats module. And the Shapiro test is a statistical test used to check the normality of the data set. And this check normality function here is taking the argument data, which is a numerical data set, array pandas. The Shapiro function is applied to the data, and it returns two values, which are the test statistic, which that's ignored here, and the p-value, which represents the possibility of observing the data if the null hypothesis is true. When I tested the normality of each individual component, so the 5 types of cancers, the p-value for each of these components, as can be seen, were greater than 0.05. And if the p-value is greater than 0.05, that means we're failing to reject the null hypothesis for each individual component. However, when I combine this data into a single list, as seen in box 35, I tested the normality of the entire data set, which gave us a significantly smaller p-value, which is telling us no normal distribution. And the reason behind that is that combining data is going to increase the sample size. Larger sample sizes make the statistical tests more sensitive. And even though these individual components may appear normal when tested separately, the combined effect might reveal non-normality due to the increase in sample size. And so these are some of the results
to make it to zoom back in.
Would it be
Zoom in.
true that like joining a couple different normal data sets that are normal around different numbers, that the joined data set would pass this test or not? I mean, I don't really know statistics, but
Well,
Can you explain what
when
you
you're joining
explain
data,
in simpler words, Jackson? Can you explain what you explain? Don't use normality, don't use statistical tests. Can you explain it in simpler words about what happens and what you tested? In simple words, like for someone who doesn't know any mathematics.
Okay. I'll see what I can do. So when I combine the data, I'm going to have a bigger sample size. And when I have a bigger sample size, you're going to have a more sensitive test. So that's what we'd be talking about here in simpler terms. The tests are going to be more sensitive if you have larger amount of data, if you have more samples. So that's basically what I'm saying here.
You're
Sorry,
saying that you will be more accurate in whatever you do if you have more data, basically, and you found a statistical way to show it. Am I correct?
Yeah, that's what we'd be showing here.
Good.
Sorry, one more request. Can you make it a bit bigger? Is what is being asked in the chat. Thank you.
Oh, sorry. No worries. Okay. And that is the Shapiro test. And I did one other test, which was the one sample t-test, which the t-test is focusing on comparing the means. I'm going to try not to get too far in the math jargon here when I'm talking about the t-test. Understand that not everyone has a background in statistics.
What are those words? BRCA, KIL.
So these were the five types of cancers there. So those were each of the 5 classes. So BRCA, KARC, COAD. So those are the 5 class names that we were mentioning. And so this one sample t-test is determining whether whether the sample mean is going to differ from the known or hypothesized is going to differ from the population mean. So that's what the one sample t-test is going to be used for. And that's what you see here is we're taking the population mean for each of these classes.
You're saying all the biomarkers, and you're trying to see whether the mean of the biomarker changes, like the entire vector.
We're just trying to see whether the mean of the biomarkers are going to differ.
Okay.
So that's what we're going to be doing. That's what we're doing here. And so this was the t-test. This is some, and then we took the sample means, and I took another p-value here. And as we can see for each of the components, the p-value is going to be greater than 0.05. And so that's what we were talking about in this first part. Do we have any other questions in this first part?
Someone asked, what does the p-value mean?
All right. Hold on. I'll explain what that means. Should I put it in the chat?
She says sure. The p-value is just like your probability value, right? And you just
So
want it.
p-value is a probability value, and it's used in statistical testing specifically.
And you want your p-value to be like over 95%. Usually you set like, or you want it to be under, whichever one. You want it to be like 95% probable to say you're there.
Mm-hmm. Yep. All right. So
Yeah, without getting too deep into all the statistics, it's a measure, it's a probability value.
Yep.
And
that's a probability value. I could get further in the details, but we may be on for a while. And this is a 4-part project, and I'd be happy to explain the other parts and try not to go too deep in the explanation. So now I can talk about the second part, which the second part of the presentation is talking about dimensionality reduction. And there were several different algorithms that I used for dimensionality reduction. So I used principal component analysis, linear discriminant analysis, and the t-distributed stochastic neighbor embedding, so TSNE. And I can explain briefly what each of those algorithms are. I don't want to get too far.
how about you pick your favorite
I don't
one?
want to just get into the jargon of it, but I can explain, or I will try to explain what I'll do. So principal component analysis, first of all, is a dimensionality reduction technique used in machine learning. And so the main purpose of principal component analysis is to transform a high dimensional data set into a lower dimensional space while retaining as much of the variability as possible. And that's what we're doing here, is we're trying to reduce. And I could talk further about how it works, but that may be getting a little bit far into the details.
Can I help? You remember there were like many biomarkers, like thousands of biomarkers.
Yeah, there were about 20,000 biomarkers there.
Yeah, and what you're trying to do is you're trying to reduce the numbers to 10 or 5 or 100 or whatever small
What I'm
number.
doing here, so I've got about 20,000 biomarkers here, and I've got about 800 different features. So 800 different features. So what principal component analysis? So we're transforming this 800 dimensional data set into something that's much lower dimensional space while retaining as much of the variability as possible. That's what PCA is doing.
Yeah.
Typically, we would be using two components.
Jackson, let me interrupt. When you're saying dimension, people don't associate it. It's the number of biomarkers you have eventually.
Wait a second. because it's 20,000 biomarkers. It's about 800 features. We're getting those 800 features, 800 components. We're trying to reduce that into a lower number while retaining the variability.
You want your data to be smaller, and the dimensionality that you started with, the number of biomarkers is your initial dimension.
Go ahead.
So the 800, those are features and not samples?
800 are the the 800 rows that we're talking about. Those are the samples there, and these biomarkers are what we have up here.
I'll help you out. In this table, the columns are the dimensions you
The
have.
columns are the biomarkers.
They're
rows
the
are the
dimensions you have. So when we say reduce dimensionality, you're trying to make a table with less columns. How you do it is the technique that you're using.
That's
And the
principal
number of
component analysis.
samples, the 800 you have, is how much data you have.
Mhm.
It's how many people you want to classify or whatever. I'm simplifying the words because if you're using the mathematical words, you lose some of our audience.
I'm going to lose some of the audience, and that's what I'm going to do here. I may have just needed to simplify this because
You're doing good. Proceed. I just interrupted so people will.
no worries. You're just trying to get some clarification here. Because I could go on and on, but I would probably lose someone talking about the math behind.
Well,
Yeah,
why do you
but-
do this? Why do you want to reduce the columns?
So why use principal component analysis?
Yeah, why are you doing it?
So in principal component analysis, the number of features will get reduced, and it's going to simplify the model, and it's going to make it more efficient. The interpretation for each of the components is going to be more clear. And PCA, principal component analysis, is useful for exploratory data analysis. And also, PCA is easier to visually explore data in lower dimensions. It's a lot easier to explore data in two or even 3 dimensions rather than explore it in 20,000 dimensions. These scatter plots could potentially reveal some patterns. And so that's why we would use principal component analysis.
Right, because you can make a 2D or 3D graph. You can't really make a graph with like 500.
You can't really make a
dimensions.
20,000 dimensional graph. You can
Yeah.
make a 2 or 3 dimensional graph, but not a 50,000 dimensional graph, because I couldn't visualize that. I don't think anyone else could visualize a 50,000 dimensional graph.
No, it reminds me of like material science or metal alloys. If you get
Maybe
more
if we're
than 3
talking material
metals in the
science, but we're
alloy,
not talking material science.
sorry,
I'm trying to talk AI and trying to explain this how
I
I
just use a
can
metaphor.
without
yeah.
without confusing anyone.
Totally. Yeah, you can make graphs and you can conceptually understand 2 or 3 dimensions, so that makes sense.
Yeah. And that's the PCA, and that's principal component analysis. And I used a couple of other different algorithms. So we tested a couple different algorithms as well. So principal component analysis isn't the only algorithm that can be used. I also looked at linear discriminant analysis. And so linear discriminant analysis is another supervised dimensionality reduction technique. And so what you're trying to do with linear discriminant analysis is to find a linear combination of features that maximizes the separation between the different classes in the data set. So the main objective of linear discriminant analysis is class separability, which is one of the reasons why LDA is a great tool for classification tasks. And the goal is to create a new feature space where these classes are well separated. And so that's what we're talking about with linear discriminant analysis.
When you're saying the word feature, to explain it to be a feature is a combination of your data, basically.
Mhm.
It's, let's say, column 1 plus column 3 divided by column 4. That's a feature.
Something like that.
Yeah, it can be many things, but
It can be many things here. Yep. And that is linear discriminant analysis. And so this is some of the code here. And as you can see, we used a k-fold cross validation to evaluate how well the model is going to perform. And it did a little bit better than the principal component analysis. I'd talk about linear discriminant analysis a little bit further in detail, but I think I'd probably lose most of y'all. And so that's linear discriminant analysis. And the third algorithm that I used was TSNE. So TSNE stands for T-distributed stochastic neighbor embedding. And in the project, they had us use all three of those algorithms, experiment with the algorithms. So TSNE is going to construct probability distributions over pairs of points in the original higher dimensional space and the lower dimensional space. And so that's what we're doing here. It's going to help users more easily visualize the high dimensional data sets. And before using the TSNE, it's recommended to use another dimensionality reduction technique like PCA. And so that's what I was doing. And when I did the TSNE fit transform, computed the samples, KL divergence stands for Kullback-Leibler divergence, which I'm not going to get too far into details on the Kullback-Leibler divergence because that would I'd lose most of y'all there. And so this is the TSNE. I don't know if you've got any questions.
What's this plot?
What is this plot? Think about it. So this is a TSNE plot here. These are the dimensions here, and these are just the points.
So what are you showing? Features compared to something else? What's the X or what's the Y?
So we're just talking about the two TSNE dimension plots. So after TSNE, we started off by putting this into 2 dimensions here, and these are each of the 2 dimensions. And so that's what I did for the TSNE.
And do the colors mean anything?
Not necessarily.
Do the clusters mean anything?
The clusters. That's just showing us that we have. That's just showing us that we have a couple different clusters.
Well, my understanding of it is that each cluster is supposed to be a class, basically, because you broke it down into 2 principal components, or I don't know what they're called in TSNE, if they're called something else. And then you can kind of visualize the classes. So each cluster should be, if it's all nice, it should be a certain classification. And you don't even need any deep learning. You have it right here. You don't
really need the deep
right
learning.
into your cluster. You just do a nearest neighbor, whatever. Can't think of all of them off the top of my head, but yeah, it's very powerful stuff. The visualizations.
It is very powerful stuff, and as I mentioned, I've got many things to learn about these algorithms.
A lot of times you'll plot the class as the color, and then you can see the homogeneity of the clusters. Is the color representing the class?
The color? Not necessarily. The color is just representing.
It doesn't look like it in this case, but I bet if you put the class, if you set the color equal to the class in these plotting, when you plot it, you'd see it much clearer. Like
Yep.
in this, you'd have to recalculate the whole Tinsney. Tinsney is kind of more expensive, I guess, but it's still probably
It can be expensive. So I would have to go back and play around with this to better visualize that. And that's something I could do at a later date. Just so we can more clearly show the class. That's something I can do here. And that takes care, that is the, that's the second part. I don't know if y'all have any questions on the second part. Or if I can just go ahead and talk about the third part.
Keep going. I don't think there's any other questions at this time.
I don't think there's any other questions here. So I'm going to talk about this third part because the third part, we're talking about clustering algorithms. And so I used a couple different clustering algorithms in this project. I used the k-means clustering, hierarchical clustering, and mean shift clustering. So I'm going to start off by talking about k-means clustering. K-means meaning the k-means algorithm. So k-means algorithm is an unsupervised machine learning algorithm used for clustering. And the goal of k-means clustering is to partition the data set into k clusters based on similarity. And each of these clusters contain data points that are similar. So you're basically breaking your data set into k groups. And I can talk more about how it works. And so what I did here to figure out how many k's, what would be the ideal number of k clusters to use, I have this graph here. So this is the elbow method. And the elbow is just telling us where would be the best case. You have an elbow around 7 clusters. I did choose 5 because there are 5 different classes that I was trying to classify here. Whether it would be one of these 5 classes, PRCA. And so that's why I did use 5. You could, according to this graph, it looks like there is an elbow around at 7. And so that's why I used the 5 classes. And so as you can see, this cluster label is telling us which column, which class is this going to likely belong to, which the classes are labeled from 0 to 4.
But this is ignoring the input classes. This is like an unsupervised method where you're trying to find a new set of classes.
Mm-hmm.
Think about it the same as asking, okay, knowing only what the data, how many types of cancers can there be, and trying to organize them without knowing what were cancers or not according to the data. This is the easiest way to explain it. It's not exactly.
That's an easy way to explain it. Yes. And k-means is pretty easy to implement, and it scales pretty well to the data sets. However, whenever you're using k-means cluster, you have to specify the number of clusters beforehand, which can be kind of difficult to determine. And these results of the k-means clustering algorithm depend on the initial centroid positions. You're assuming that these clusters are fixed, and you're assuming that you have fixed spherical clusters for the k-means algorithm. Because even if you have outliers, that can mess up the k-means clustering algorithm. And that's one of the disadvantages of using k-means. And so as we can see, you've got your 5 clusters here, 0, 1, 2, 3, and 4. And so this is the graph, and I can zoom this out a little bit just so we can all see the graph.
What are the columns here? Those are like the features you calculated before?
Yeah. So these are the feature columns 1.
So this is with the TMNE algorithm, you created 2 columns?
Let me look at this.
Yeah.
Yeah, this was from the XTSNE. So this was a pandas data frame from the XTSNE algorithm that I was talking about before. So I was continuing on with that data frame for the k-means. And so that's where you have your column 1 and your column 2. So so answering your question, Jacob, that's where those came from. Because as I mentioned before, it's a lot easier to visualize something in 2 dimensions than it is to visualize in 20,000 dimensions.
So when trying to figure out like what number of classes, minimizes your error, like is it, I don't know much about like dimensionality reduction, but is that pretty typical for k-means that you would, is that more for visualization, or is that like a standard thing that you would do?
Can you repeat the question, please? Sorry.
Basically figure out the number of clusters.
Well, you do have to specify the number of clusters beforehand when you're using the k-means clustering algorithm. And you may not always know what is the ideal number of clusters. So that's why I've used this elbow method graph here to help me determine what would be the best number of clusters to use. I used 5 because there were 5 different kinds of cancers that we're talking about. There were initially 5 different kinds of groups, but as you can see here, you have a little bit of an elbow around 7 as well. And the elbow method's pretty helpful to determine how many classes or what you should assign K to.
Thanks.
Not a problem. And so I can next talk about the hierarchical clustering method. So hierarchical clustering is another unsupervised machine learning technique used for clustering analysis. And the hierarchy is created by recursively merging or dividing data points based on the similarity. And so when we're talking about hierarchical clustering, you've got 2 approaches, which you can go bottom up, which is the agglomerative approach, and you can go the divisive approach, which is top down. And I can explain briefly what I mean by bottom up clustering versus top down clustering. So when I talk about bottom up clustering, I'm starting with each data point as its own cluster, and I iteratively merging the similar clusters. And when I'm talking about top down, I'm going to start with all the data points in one cluster and recursively splitting them into the smaller clusters. And as you can see here, I'm going to try and get this. As you can see here, the result is a dendrogram, which is going to visually represent the cluster hierarchy. So when we're going bottom up, you're just starting with each of the data points as their own clusters, and I iteratively merging them. So when we're going bottom up, that's agglomerative, and when we're going top down, you're going to start with all data points in one cluster, and recursively splitting them into smaller clusters. So this is what I'm talking about with the dendrogram. Hierarchical clustering does result in the tree-like structure, which makes interpretation a little bit easier. And it's easier, it's advantageous because you don't necessarily need to specify the number of clusters beforehand, unlike the k-means algorithm. And these dendrograms, they provide good insights into the data's hierarchical structure. And so that's what you have with this dendrogram here. And this is just a random sample of 10 points here. That's hierarchical clustering. Are there any questions on the hierarchical clustering or?
Cool. I've never seen the hierarchical clustering before, but question back to the k-means. Do you ever take the error between what it says the cluster is and what what it says the class is and what the actual class is?
So the distance. That is something I'd look into a little bit further, is to see what is the error here? What is the difference between what the class says?
Yeah.
That'd be something I'd look into doing in the future.
Don't do this. The
Why not?
difference between unsupervised and supervised is if you're using knowingly what your data is, then you're doing supervised learning.
If you're knowing what your
Well,
data is,
The unsupervised is something that you just ask, oh, here's the data,
necessarily
tell me
labeled.
something about it. You cannot, once you mix supervised with unsupervised, then you're basically doing
it's
supervised.
supervised.
So
Yes. But it would be nice to know that, oh yeah, this is, well then how do you ever measure it? How do you say, oh wow, this is actual just garbage or this is working? You have to measure it eventually.
This is machine learning voodoo. How can I tell it in other
It's
words?
not quantum mechanics. You can measure things. They don't
That is a good question there. How would you measure that?
Well, the cluster could represent something totally different than what you were trying to learn.
True.
That's true. And like I said, I've got plenty more to learn about this. This is the first machine learning project that I've done and that I've presented. Obviously, I'll learn more as I continue on. And so that's hierarchical clustering. I'm going to talk about this about the third type of clustering algorithm that I used, which was the mean shift clustering algorithm. Which means shift.
Can you zoom back in again? Sorry. Thank you.
Did y'all have any questions on the clustering?
No, it was just the font size. Thank you.
Okay. And now I can talk about mean shift briefly. So mean shift is an unsupervised clustering algorithm used for density-based clustering. And the advantage of using mean shift over k-means is k-means clustering is assuming that you have spherical clusters. And mean shift, it can handle clusters of arbitrary shapes and sizes. And mean shift, yeah, you're mainly using mean shift in computer vision. And so this cluster labels what class you may think what class it may be part of, what class it's predicting, the column 1 and column 2. Those columns do come from the mean shift cluster data. And that's coming from this TSNE data as well. And so this is another cluster graph of mean shift. What you have here. And that's mean shift here. I don't know if y'all have any questions about mean shift.
Yeah, so it seems like mean shift is more accurate than k-means. Is there like a penalty in time complexity?
Of using mean shift?
Yeah, compared to the k-means or one of the others.
So if your data set is larger, the mean shift algorithm can be quite slow.
Yeah.
And also there's a bandwidth sensitivity for the mean shift clustering algorithm because the results that you get on the mean shift clustering algorithm depend on the choice of bandwidth that you choose. And also mean shift algorithms do require the strong pairwise distances between the data points.
So it seems like a trade-off speed for.
There are some advantages and disadvantages between using the k-means clustering versus using hierarchical versus using the mean shift clustering algorithms.
Yeah, I mean, the spherical assumption seems like a pretty bad assumption. It seems like. Cool.
All right. And so this fourth week here, so the fourth part and final part is talking about some of the machine and deep learning techniques that I used, which were support vector machines, the random forest, and the deep neural networks. And so I'm going to start by talking about the support vector machines model. And support vector machines is a powerful supervised machine learning algorithm used for classification, regression, outlier detection. And it is quite versatile. As you can see, it is a pretty versatile algorithm. I separated because I put about 25% of the data into test, and then 75 in training is what I have here. That's what SVC is, the support vector classifier. And I got a pretty high accuracy for the support vector machine, and that's one of the advantages of using the support vector machines, is that this algorithm does perform very well in the high dimensional space. Support vector machines are also great because they only use a subset of training data, which are the support vectors. And it also works. It's great for text classification, image recognition, etc. Now, some of the disadvantages of using support vector machines are that they can be pretty complicated. It can be very difficult to choose the right kernel and the right hyperparameters to tune. SVM is not necessarily the most transparent algorithm, and it can be quite hard to interpret. And like for any large data set, training it can be quite slow. And even if we have outliers involved, that can affect our boundary here. And that is the support vector machine here. And so support vector machines do focus on finding the best decision boundary, is what you're doing here. So I wonder, do y'all have any questions on SVM? I might have lost y'all.
We're here. It's good.
That's talking about support vector machines. If y'all have any questions on it, I can talk about the other two algorithms that I was discussing. And so I can briefly explain what I mean by ROC AUC, which is receiving operating characteristic area under the curve. And that's a metric for evaluating how well classification models perform. And this score is going to quantify how well the model can discriminate between the positive and negative instances across the classification thresholds. So the ROC AUC score, it ranges from 0 to 1, where obviously 1 is perfect. At 0.5, you're just randomly guessing, because according to this support vector machines, I had a pretty good ROC score here, and it visually represents the trade-off between the true positive rate and the false positive rate at the different classification thresholds. ROC AUC is pretty useful when comparing different machine learning models, is what you're doing there. And so that's the support vector machines. The second part, see, we got a pretty high accuracy with the support vector machines. So random forest is another supervised machine learning technique used for classification regression. And it's similar to an ensemble of decision trees, which combine their predictions. So ensemble meaning group of decision trees, which will combine the predictions to create a robust and accurate model. And why random forest is good and why that works is that it's robust. This algorithm is good when working with large data sets with numerous features. The most important features are identified, which will help with the feature selection. And random forest is also quite good at dealing with the missing values. And since we're aggregating multiple trees, we're not just aggregating one decision tree, we're aggregating multiple decision trees. And since we're aggregating multiple decision trees, overfitting is avoided with random forest. Like the SVM, random forest algorithm can be challenging to tune these hyperparameters, and it's not the most transparent algorithm either. And for these larger data sets, training can be very slow. Random forest does work well with the diverse data sets. So this is the random forest. Food did pretty good with random forest as well. And now the third part, if there are any questions on the random forest. Or if I can talk about the third part. Any questions on random forest?
Nope.
All right, so I'll talk about this third and final part. So the third part, we're talking about deep neural networks. Deep neural networks, and now we're getting more into deep learning here, which deep learning, it's inspired by the human brain. And DNNs consist of interconnected neurons that process information hierarchically. And DNNs are used for tests like image recognition, pattern recognition, natural language processing, etc. DNNs are really good at learning new features from the raw data, which capture the complex relationships. And you don't need a whole lot of feature engineering as well. DNNs can handle the large data sets and high dimensional inputs pretty easily. And you can even pre-train DNNs for specific tasks. However, training these deep neural networks does require a significant amount of computational resources. And if we do not properly regularize the DNNs, they can overfit. Interpretability can be quite challenging due to how complex DNNs are. And then for effectively training a DNN, you're going to need a large labeled data set as well. And I can talk a little bit more about this, about the architecture design here of the deep neural network. So the feed-forward neural network, so the neural network is created and it has multiple hidden layers. So as you can see here, you've got several sets of hidden layers, and each of these layers have a specific number of neurons units, which would be this number here. The output layer has as many neurons as the number of classes in the problem. And so these are the sets of hidden layers. And so when I compile the DNN, you're going to choose an appropriate loss function based on the problem type, whether you have a classification or regression problem, and also to specify an optimizer to update the model's weights during training. And for this optimizer that I use the atom optimizer.
Jackson, there were some questions about what is overfitting.
What do you mean by overfitting? Yep. When you're trying to memorize the data set there.
The deal about overfitting is you end up memorizing and you don't guess well.
You're not going to guess well. You end up memorizing the data set.
And then you don't guess or interpolate very well between data points at that point.
Your network is really good at the training data, but it's really bad at real data. That's basically what happens.
That's what happens when you're overfitting, is that it memorizes the training data and you think, okay, you've got a good accuracy for this training data. But when you apply that algorithm to real life data, you're going to wonder what gives. Why isn't
it's like cramming for a test. You cram for a test, you know all the answers to that test, but if someone asks you a question that's not on the test, you're not going to know the answer.
Exactly.
That's a really good.
When you're just looking at the review and just memorizing the answers on a review, for example, and then you get asked another question that is not on that review, and then you're just left in the blind here. So that's what we mean by overfitting. Yeah. That's a good that's a good analogy for overfitting.
Thanks.
And after compiling this model, you're going to fit and train the model as well. All right. Sorry about that. And so after we compile the model, you're just going to fit and train the model. And that's what we're doing here. I'd try to run it on 50 epochs, which obviously it's going to be a little bit faster to train this on fewer epochs, 10 epochs. But it may not be as accurate with 10 epochs. You've got a loss of 2.97 for 10. And then here you've got a summary of the model. You're talking about all your layers. You've got the layers. And you've got the output shape, the parameters. All right, epoch.
I'm sorry, can I ask how many hidden layers are you using and how many nodes in total has the neural net?
Okay. The first question that was asking is what is an epoch? So when we're talking about epochs in deep learning, an epoch is referring to one complete pass of the entire training data set through this learning algorithm. And during an epoch run, the model's processing every training sample in that data set and it's adjusting the weights and biases based on the calculated loss or error. And then how many layers, nodes? I'm going to look at this. So I'm going to look at how many layers I've got. I've got a couple of layers here. I may just have to count this up and just see how many I've got.
I think you have 3 layers, the 3 dense layers,
Yep.
the others are
You've got
just
the 3 dense
released.
layers.
And one of them, the output one is the class, and the input one is all the features that you have. So
Yep. And then for nodes,
this depends on the size of the data. Don't go start arguing there. It's like the
It's
number of
gonna depend on the
parameters is
data.
shown here. This is
Mhm.
how big it is.
yep.
So yeah, I'm just curious, how did you selected the number of nodes, because it has to go relate as people were asking about overfitting. You cannot add a lot of layers and a lot of nodes if it goes beyond the number of training rows that you have. Otherwise, the network will just memorize what you have there.
Alfredo, you can.
Excuse me, you what? You can what? I mean, my understanding is that if you add, for example, if I add 100 hidden layers, and each hidden layer with 1,000 nodes, and the multiplication of that is higher than the
100,000. If you multiplied 100 times 1,000, then you'd have.
Yeah, if that number is higher than the number of training rows that I have, the neural net doesn't do anything. It just memorizes.
It'll just memorize. I'd have to look a little bit further into that and get back to you, Alfredo, regarding this.
Okay, I drop it. Okay, cool.
You've got some good questions, Alfredo.
No, just
And I'd be happy to discuss this further.
My question was, because I'm not familiar with this package exactly, is there any kind of does the package already automatically select the number of nodes for you? Or how did you come up with the number of layers and the number of nodes?
How did I come up with the number of nodes?
Yeah.
So if we're looking, I'm going to go back up and just show you what I mean. So how did I come up with these numbers here? Are you asking about how I came up with these numbers here?
Guys, I suggest that we cut off the questions because it won't be the recording. Alfredo, let's keep it out if possible. I already lost connection.
I think we're probably we can discuss this in another we can have a further discussion about this.
Well, I think your
I would
input
look
shape
at
and your
this.
output shape are kind of important.
Mhm.
Your input shape, you don't get to pick. You've set it to 2000, whatever it is.
Mhm.
And that was because that's your number of features.
Yep.
And you have an output shape of 5 because you want to do 5 classes.
Yeah, you want to get the 5 classes, so that's why the output shape is 5.
But then everything in between, why he picked 500, you probably just made them up. Like that's what,
Yeah, I made up the numbers.
yeah, it's fine. You can keep going.
Alfredo, we can discuss this at a later time, on a
No
later
problem.
date.
I'm satisfied. I
can
just
look at
wanted
this.
to know if the package already provided some help for you to estimate that, or that's it. Thank you. Yeah.
Yeah, you had some good questions, and like I said, we can discuss this further if you like. And so what I'm looking at here now is we're looking at our accuracy of this model here. And as you can see, I'll make some adjustments to this to see why the accuracy model isn't as great as I'd hoped here.
And that accuracy graph was on the training set
This side,
or on both the training and the testing set?
let me look at this. I think that's the training. Yeah, that's the training. I'm gonna look at that and see if that's the training or if that's the test here. So this was training. Is what this one was.
Makes sense.
Yeah, that was training. And so I now ran it through with the test data as well. And obviously my training accuracy is a little bit higher than the test accuracy. My accuracy wasn't that great on this network, and I'll admit that I do have plenty to learn about this. And once I learn more about deep learning, I'll make further adjustments. And so at the end, I print the classification report, and then I run the and then I print the ROC-AUC score. My score obviously wasn't as great as the random forest or the SVM.
Guys, I'm asking just because of technical difficulties. We want to wrap it up so we'll finish the recording.
Okay.
Jackson, can you wrap it up? I apologize, but
Yeah, no worries. We
it's
can wrap
impossible. I
this
already
up.
lost connection once.
That was training, yes.
It's usually we can continue asking questions, but I want to just finish the recording part if it's okay.
Okay. Okay. I don't know if y'all have any other questions.
No more questions if there aren't any. I'll just stop the recording. We do want to applaud you. I just technically we cannot. We can continue questions afterwards, but let me stop
Yeah,
the
we
recording.
can continue. We could continue discussing and talking about questions afterward.
I do want everyone to thank you because you finished presenting everything, correct?
Yeah, that is the end of the presentation there.
Okay, so let's thank you all. Actually, thank you, Jackson. It's really nice, and thank you for all those who stayed. You had a very nice number of people watching.
I appreciate
I'm
the
going to
support.
stop
Thank you all.
recording now.
All right, thanks.